Hi, this is Satyajit. This video is an extension to the previous topic, optimal text searching in BWT-runs Bounded Space. However, this time we're going to go in a little more detail about how the lemmas are supposed to work. Starting off with lemma 2, states that we can store O of R words such that for a given pattern, we can find out the uh, interval of the suffix array from starting position to the end position of all occurrences of p in t, and this can be done in time O of m into log of sigma plus n by r to the base w. Uh, in this process, we'll also return the position p and the content suffix array of p of at least one cell in this given interval. Moving on, so the most fundamental part of lemma 2 is a data structure which is called RC. So RC stores all the occurrences of character C in a BWT array. So it is something like a pair over here. So P is the position of this character in the BWT, and SA of P minus 1 gives us the actual position of the character C in the original text. So this is how it is stored. One thing to note here is that one character can appear multiple times. So if you're talking about something like AAA, BBB, AAA, you have two characters, but you have three different runs. So A would have two different positions of the character in this original text at the second part of this pair. So in turn, what this means is the overall space required for these structures is proportional to O of R, which is the number of runs that we have in our Burrows-Wheeler transform. So one concept, so a couple of concepts that the authors give us here is that the empty string is a suffix of all text positions. So this is quite intuitive. Eventually, this interval, the interval of characters in the BWT that immediately precede occurrences of the empty string spans the entire BWT. So for an empty string, the preceding occurrences are covered in the entire BWT. So connection to the P of M, which is the last character of a specific pattern in the text T. So the last character that we mentioned must appear in the BWT as the last character of some run. So if the pattern P exists in T, then PM must appear in the BWT, because BWT is just a transform of this text T and it appears as the last character of some run. This is because BWT has this nature of characters having a preceding suffix form of contiguous runs. So the goal is to find the position of the suffix from P of J all the way to the last index of a pattern in the suffix array SA using the BWT and the predecessor queries that have been mentioned previously. So predecessor queries has been mentioned in the previous paper by this author, and so it essentially calculates the time in O of log time complexity. So imagine you are matching a pattern from P of J all the way to M, and you know the interval of P of J in uh, within the interval S of and the interval is within S of SP and EP, the start point and the end point. This means that uh, the rows starting position to end position in the suffix array correspond to the suffixes, or to all the suffixes that start from the P of jth index all the way to P of M. Now we come across two scenarios here. Now at this stage we're checking for BWT of P And if BWT of P is equal to P of J, we apply LF mapping uh, to get the previous position in the next iteration. So if this specific uh, character is matching, we proceed with our retrieval and we apply LF mapping to move one step back. Uh, and however, if we don't come across BWT of P being e- equal to P of J, and uh, one thing to know here is that P has to and P occurs in T, then there is still a valid interval SPNP, which should have this P of J. Um, and in that scenario, what we could do is we could use a predecessor query to find the position P dash and its corresponding value in the suffix array. This is where the sample character comes into play. Sample characters are at the boundaries, and if P occurs in T, then we can find the boundary of a specific run, which is where the predecessor queries can help us to find the position P dash. So, all in all, adding both of these scenarios, considering P occurs in T, once we have computed the interval of P all the way to J of P from the jth index all the way to the end of it, we can use LF mapping as well as predecessor queries iteratively to find the position and the content of at least one cell in the corresponding interval of the suffix array. So these two are used interchangeably. So once we've defined RC, lemma 2 does something more apart from just storing RC. So the idea is to get a larger data structure which efficiently manages the positions of all characters across the BWT. So um, not just C character, not just the individual characters. We look at the entirety of the string. So we have to efficiently manage the positions of all characters across the BWT. So we define a single structure R that covers this combined universe of size sigma into n. Um, so in RC, each element is indexed as P, which is the position in the Burrows-Wheeler transform, and SA of P minus 1, which is the position in the text, as we had mentioned before. So we transform each pair such that we get a new pair, which gives us the corresponding uh, corresponding position in the Burrows-Wheeler transform as well as the position in the larger text in this format. So we're not dealing with a smaller structure. We can just store C, we can store N, and we can get the value of all. We can get the value of we can get the value of the position of the text for every single run in our Burrows-Wheeler transform using this newer structure. So previously, so predecessor search is a query that we had conducted on our previous RC structure, but for an R structure, the larger data structure, we need a modified version of this. So um, as we concatenate all the RCs into a single R, we have to now perform something called R into C minus 1 of N plus Q. So we have C, we have N, and we have Q. Then we just have to find out what specific character this is, which number is this, and which specific uh, character we are trying to find. And eventually we get this result back and we convert it back to the original RC, so indexing becomes more convenient in this way, and effectively we just have to store O of R words and The predecessor data structure uh, that they had mentioned in the previous paper, it takes around this much time. So uh, yeah, so this lemma 2 holds true for this scenario. Okay, so moving on to lemma 3. uh, Lemma 3. So the main objective here is, if we know the suffix array at position p, we want to find the suffix array at position p minus 1 and p plus 1, which is the preceding and the succeeding uh, suffix array positions. And this is in correspondence to the position in the text T of the Burrows-Wheeler transform of p minus 1 and p plus 1. So if we know BWT of p, we should find a way to know BWT of p minus 1 and BWT of p plus 1. However, the most important objective here is to find a way to store O of our words for a bigger text over alphabet uh, numbered sigma, where R is the number of runs in the BWT. And uh, so eventually, if we have these O of our words, we can count the occurrences of P in T uh, for a given pattern in the larger text in O of M of log of sigma plus n by r to the base w time. And after counting, we can also report the occurrences locations in overall time, which is O of occurrences into log of n by r to the base w. So there is a predecessor structure P of plus minus, which locates I, which is the starting position of the phrase containing T of K. Um, so this character is a representative of BWT of P. Let's suppose. So this is efficient due to the properties of P plus minus. This has been discussed in one of the previous papers. Additionally, there's one more data structure, which is the metadata of n of I. Uh, it stores x and y, where x is SA of q minus 1. So it stores the preceding position of q in the suffix array and the succeeding position of q in the same suffix array. So we want to know how and why this works. So there have to make there have to be some assumptions as well here. So SA of p minus 1 is set to j plus 1, and SA of p plus 1 is set to l plus 1. So moving back, we had SA of p is equal to k plus 1. So keeping these three things in mind, we can move ahead with our proof. So from these two above statements, j and l are the positions of uh, BWT of p minus 1 and BWT of p plus 1 in the text T. Uh, Another thing to note here is, for all occurrences of T up to this range of k minus 1, k minus I, uh, I being our position, we have to know that T of k minus T is not the first nor the last character of a run in BWT. Thus, by applying LF mapping, we have to find LF of p minus 1, LF of p, and LF of p plus 1, which corresponds to the BWT positions of T of j minus T and T of k minus T, as well as T of l minus T. We find out that these are contiguous and within a single run. Thus, we can also conclude that T of j minus T is equal to T of k minus T, which is in turn equal to T of L minus T. Moving on, so for T is equal to K minus I minus 1, we can extend this equation in a way that T of J of K minus I minus 1 is equal to t of I plus 1 and t of L minus ki minus I plus 1. So these all have to be contiguous in the Burrows-Wheeler transform. So this LF step eventually gives us BWT of Q that is equal to T of I, which also helps us to find BWT of Q minus 1 and BWT of Q plus 1. Correspondingly, once we have BWT of Q minus 1 and BWT of Q plus 1, we can use the other data structure to find out SA of Q minus 1 and SA of Q plus 1. Since BWT and suffix array are corresponding to each other, we can maintain our second data structure n of I such that we can find out SA of Q minus 1 and SA of Q plus 1, assuming that we have have the value of SA of Q. We enter lemma 4. Lemma 4 is something that is based on lemma 3. It is an extension of lemma 3, just that lemma 3 just looks at the previous and the next position, while lemma 4 extends that to S positions. So there's a concept called run breaks in the BWT. So this helps us to retrieve all the suffix array positions efficiently from distance q, and if you have SA of Q, you can find SA of Q minus S, and you can find SA of Q plus S, and all the all the characters all the values in between. So more about run break. A run break occurs when the character in the BWT changes. So this change divides the runs of repeated characters. So we sample specific BWT prepositions. We've discussed sampling previously. So sampling in this scenario is done at fixed intervals. So like I mentioned, if you want SA of Q minus S and SA of Q plus S, S is the specific fixed interval that we set. We also make use of predecessor data structures. So this is something that we use for locating sampled positions more efficiently. Predecessor data structures is just something that we covered in lemma 3, p plus minus, except in this case we have the predecessor data structure look up to S positions and not just the previous and the next one. So essentially this is not in the multiples of O of R, but rather O of R into S. Again, we have something called skipping of contiguous ranges. We use LF mapping to skip contiguous or unary ranges in the BWT. LF mapping is something that we also stated as a prerequisite for this. So there are two data structures that we use. Like I mentioned, the second data structure is P plus and P minus. We have O of RS size instead of O of R that was used previously. So that is one of the main points of discussion here. One more data structure is the W data structure. It runs from 1 all the way to the position T. It maps sampled BWT positions to their corresponding positions in the given text. So for every single I, we store P plus and P minus for its position in W. So essentially when you get W of F of I, it gives us the position back. Eventually, to answer queries given a specific position in the suffix array, that is SA of P, we first get the P plus and P minus, and for I less than SA of P, in O of log of n by R time, we can retrieve F of I, and then once we have this F of I, we can use SA of P plus J, which is F of W of F of I plus J. So P corresponds to F of I. Then we have got P plus J becoming F of I plus J, plus SA of P minus I for all the positions from J is equal to 0 all the way up to our sample number, which is S. There are two scenarios which might occur here. The first is when P all the way to P plus S has two distinct characters. That is when a run break occurs. So essentially, you have a boundary. You have got SSS and then you have got PPP. So you've got a boundary S and P. So this range ensures that SA of P, P plus minus, and all position P of P plus S maps directly to a contiguous range in the W data structure that we had uh, noted down before. So this is supposed to work mostly with multiple characters. However, sometimes we might encounter a unary range where all the characters in a specific run are the same. So the range has just a single repeated character. In this scenario, what we would do is we would apply LF mapping iteratively to skip all the unary ranges until we find ourselves in the case 1 scenario. So unless we find that in our range we have multiple characters, we can iteratively apply last to first mapping. Once we do that, we essentially reduce our problem to the case 1, and the values again can be retrieved from our data structure W. I think that was all for this video. I hope you understood what I was trying to convey. Thank you.